Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 5th, 2026, just about a week ago. It identifies a fundamental problem called the ambiguity of attribution, where researchers struggle to know if performance gains in multi-agent systems come from smart collaboration or just throwing more compute at the task. To fix this, it proposes a rigorous framework and a new metric called collaboration gain. The paper is titled, Towards a Science of Collective AI LLM-based multi-agent systems need to transition from blind trial and error to rigorous science. And as we'll see later, the proposed framework offers a much-needed roadmap for systematic improvement rather than random guesswork. To visualize this shift, Figure 1 contrasts the status quo with the proposed framework. On the left, the current paradigm is depicted as a black box process, essentially a game of dice where improvements are random and unexplained. The right side transforms this into a rigorous scientific workflow. Here, researchers deliberately select variables from a structured factor library, like agent diversity or communication mechanisms. The crucial element is the prism at the bottom, representing the collaboration gain metric, gamma. This prism takes the observed performance and optically separates mere resource accumulation from true collaboration gain, ensuring that we only validate factors that genuinely make the system smarter. So, Figure 2 makes this metric concrete by plotting performance against the total computational budget, which is essentially the cost in tokens. The light blue curve represents the single agent baseline, which naturally plateaus even as you add more resources. In contrast, the dark teal spiral tracks the multi-agent system. The critical insight appears on the right side, where gamma exceeds 1. Here, the multi-agent system breaks through the single agent ceiling, proving that the performance boost comes from genuine synergy rather than just spending more budget. Alright, having established the metric, Figure 3 lays out the factor library taxonomy. This diagram organizes the variables researchers can tweak to achieve that collaboration gain. On the left, we see the task context, or external factors, which includes attributes like task decomposability and sequential dependencies. On the right side, the internal multi-agent system construction is split into 2 layers. The control level defines the static architecture, such as organizational structure and communication mechanisms, while the informational level tracks dynamic behaviors like content entropy and evolutionary distance during runtime. To ground these theoretical factors in reality, Table 1 reviews the biological roots of collective intelligence algorithms. It lists classic methods like ant colony optimization and particle swarm optimization, which map directly to behaviors observed in nature, such as ants following pheromone trails or bird flocks coordinating flight. The table categorizes these into domains like search and optimization or robotics control. This historical context highlights that effective multi-agent systems have always relied on mimicking specific biological mechanisms, reinforcing why a structured library of these factors is so essential. Moving from theory to practice, Figure 7 applies the collaboration gain metric to evaluate 2 different organizational structures across 3 datasets. The vertical axis measures gamma, where the dashed line at 1.0 represents the break-even point for a single agent. The blue bars show that a linear chain topology consistently scores above this line, proving it generates positive synergy. In contrast, the orange tree topology bars fall below 1, which reveals that for these specific tasks, the overhead of coordinating branching paths actually degraded performance. Well, while the previous figure focused on topology, Table 6 quantifies the impact of model heterogeneity. In this experiment, the multi-agent system assigns a specialized coding model to the programmer role, rather than using a generic one. The results are striking. The composite quality score, labeled Q, nearly doubles from 0.27 to 0.50. Crucially, the gamma metric on the far right hits 1.85, which confirms that aligning specialized models with specific roles creates a massive nonlinear leap in performance. Wrapping up, 2 takeaways stand out. The field must graduate from blind trial and error to rigorous measurement, and the collaboration gain metric provides the standard needed to do so. By isolating true synergy from mere compute scaling, this framework paves the way for a genuine science of collective AI. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.